In the cold, silent depths of space past the orbits of Mars and Jupiter, a solitary traveler completed its final poignant journey. The Cassini spacecraft, a marvel of human ingenuity, had spent 13 years unveiling the majesty of the Saturnian system. It had shown us rings of impossible thinness and storms larger than our own world. Yet, its most profound discovery orbited not the gas giant itself, but was a tiny moon, no wider than the length of England, a sphere of brilliant, pristine ice named Enceladus. On its last daring passes, Cassini dove through a ghostly mist, a faint exhalation from this diminutive world. This was a spray of water erupting from deep fissures in the moon's South Pole scars, on the ice that scientists had poetically named the tiger stripes. These colossal eruptions blasting ice crystals at supersonic speeds into space were a spectacle that defied all expectation for such a small frozen body. They hinted at an impossible secret hidden beneath miles of solid ice, a warm liquid, and potentially life-bearing global ocean. The discovery transformed our understanding of where life might exist, but it also presented a heartbreaking paradox. The very violence of these cryovolcanic jets, this constant outpouring, suggested Enceladus was losing its precious internal sea at an alarming rate. Early calculations painted a picture of a transient ephemeral world, a fleeting oasis in the cosmos, destined to freeze solid in a cosmic blink. Its ocean, the very thing that made it so compelling, appeared to be a temporary feature, its life-giving potential doomed by its own spectacular display. But science is a story of revision, of re-examining what we think we know. Deep within the final data streams sent back by the dying Cassini probe, a new truth was waiting patiently to be uncovered. A revelation that suggests the heart of Enceladus is not fading but is beating with a slow, steady and ancient rhythm. The ocean of this tiny moon may be far more stable, far more enduring, and therefore far more promising than we ever dared to imagine. Our journey to this understanding begins not with Cassini, but decades earlier with the fleeting glances of the Voyager probes. In the early 1980 seconds, Voyager 2 swept past Saturn, its cameras capturing the first close-up images of Enceladus. What it revealed was intriguing but ultimately underwhelming. The moon was the most reflective object in the solar system, a brilliant white sphere that bounced almost all sunlight back into space. It showed regions of ancient heavy cratering, alongside smooth younger plains, a geological dichotomy that hinted at past activity. But to the instruments of the time it appeared a static, frozen artifact, a geologically dead world locked in a deep celestial slumber. For over 2 decades that remained the consensus. Enceladus was a footnote in the grand textbook of the solar system, a bright but uninteresting companion to the glorious rings of Saturn. Then came the Cassini-Huygens mission, an audacious international endeavour, the most sophisticated robotic probe ever sent to the outer solar system. It arrived at Saturn in 2004, armed with an arsenal of advanced sensors, ready to spend more than a decade peeling back the layers of this complex system. In February of 2005, Cassini made its first targeted flyby of Enceladus. Scientists expected a routine survey of a quiet, icy moon. What they found would ignite a revolution in planetary science. The magnetometer, an instrument designed to measure magnetic fields, detected a strange and significant disturbance around the moon. The field lines of Saturn's enormous magnetosphere were being draped and bent as if they were encountering an obstacle, a hidden atmosphere. But how could a world so small, with gravity so weak, hold onto an atmosphere? It was a profound anomaly, the first clue that Enceladus was anything but dormant. Subsequent passes brought more puzzles. The spacecraft's instruments detected a cloud of neutral water vapor densest over the moon's southern polar region. Thermal imagers registered unexpected hotspots, areas of the surface that were significantly warmer than the surrounding terrain. These thermal anomalies were concentrated along the tiger stripes, those 4 parallel bluish fissures gouged into the south polar ice. The evidence was mounting, pointing towards a conclusion so extraordinary that many in the scientific community were hesitant to embrace it. The team controlling Cassini's cameras decided to take a risk. They programmed the spacecraft to look back at Enceladus as it flew past with the sun illuminating the moon from behind. This specific geometry, they hoped, would backlight any fine particles, making them visible against the blackness of space. In November 2005, the images arrived back on Earth. They were breathtaking. There, erupting from the moon's southern limb, were multiple towering fountains of ice glittering in the sunlight. They were not wisps, but focused collimated jets blasting hundreds of kilograms of material every second into the void. Enceladus was alive. It was a world venting its internal ocean into space. The sterile, frozen footnote had transformed overnight into the most compelling astrobiological target in our solar system. The shockwaves of this discovery are still being felt today, fundamentally altering our search for life beyond Earth. The implications were and are staggering. It meant that a moon 1.5 billion kilometers from the Sun, in a region of perpetual deep freezing cold, possessed a source of liquid water and a powerful internal heat engine. To truly grasp the significance of these emanations, we must journey deep beneath the moon's frozen crust. Imagine an immense spherical shell of ice, perhaps 20 to 30 kilometers thick. It is a barrier of unimaginable cold and pressure. Yet below this solid rampart lies a vast, globe-spanning body of liquid water, an ocean deeper than any on Earth, warmed not by a distant sun, but by the relentless gravitational tug-of-war with its parent planet Saturn. This process, known as tidal heating, kneads and flexes the moon's rocky core, generating immense friction and consequently heat. This geothermal energy warms the water at the boundary between the rock and the liquid, creating the conditions for one of the most exciting possibilities in all of science: hydrothermal vents. On the floor of Earth's own oceans, in the crushing blackness of the abyss, such vents are teeming oases of life. They are chemical furnaces spewing superheated mineral-rich water into the sea. Life here doesn't rely on sunlight for energy. Instead, microbes perform a process called chemosynthesis, harnessing the chemical energy of compounds like hydrogen sulfide and methane. These microbes form the base of a complex food web that thrives in total darkness. The data from Cassini's flight through the Enceladus plumes suggests that a similar process could be happening there. The spacecraft's instruments tasted the spray, analyzing its composition. They found not just water but salts, proving the liquid's contact with a rocky core. They found silica nanoparticles, tiny grains of sand, that can only form in water heated to at least 90 degrees Celsius. This was the smoking gun for active hot hydrothermal vents on the seafloor. And then they found the ingredients for life itself. The plumes contained methane, carbon dioxide, ammonia, and a tantalizing array of complex organic molecules. Most crucially, during one of its final deepest dives, Cassini detected molecular hydrogen, a potent source of chemical energy. On Earth, hydrogen is a preferred food for certain types of microbes. Its presence in the plumes of Enceladus means that a potential food source is being actively supplied to the ocean from the moon's core. All the essential ingredients as we understand them, liquid water, a source of energy, and the right chemical building blocks appeared to be present. A hidden, habitable realm was no longer a matter of pure speculation. Let us construct an analogy to better visualize the mechanism of these eruptions. Picture a colossal planet-sized bottle of sparkling water buried deep beneath a thick crust of ice. The sparkling water represents the subterranean ocean, and the fizz, the dissolved gases like carbon dioxide and methane, kept in solution by the immense pressure of the overlying ice shell. The rocky core at the bottom of the ocean is being constantly heated, acting like a stove burner, keeping the water warm and churning. This heating process also releases more gases from the rock, further carbonating this abyssal realm and increasing its internal pressure. The tiger stripes on the surface are like tiny cracks in the cap of this bottle. As Enceladus orbits Saturn, the gas giant's gravity stretches and squeezes the moon. This tidal flexing periodically pries open these fissures, these tiger-striped cracks. Suddenly, the immense pressure of the deep ocean finds a path to release. As the pressurized gas-rich water surges upwards through the crack, the pressure drops dramatically. The dissolved gases instantly come out of solution, forming bubbles with explosive force, just like opening a vigorously shaken soda bottle. This process, known as effervescence, creates a frothing, accelerating mixture of liquid and gas. This foam rockets up through the fissure, freezing as it goes, and erupts into the vacuum of space as a fine mist of ice crystals and water vapor. This model, the effervescent eruption theory, elegantly explains how a world with such low gravity can shoot plumes hundreds of kilometers high. It is not a simple geyser of steam, but a complex gas-driven cryovolcano. But this beautiful, violent mechanism presented a profound problem. Based on the initial density readings from Cassini's instruments, scientists calculated the total mass being ejected from the South Pole. The number they arrived at was astonishing, roughly 200 kilograms per second. It is an amount of material equivalent to a large iceberg being blasted into space every year. When they modeled this rate of loss over geological timescales, the conclusion was stark and deeply troubling for astrobiologists. At this rate, the entire ocean of Enceladus could be depleted in as little as a few 100 million years, perhaps even less. This led to the transient ocean hypothesis. Perhaps the activity we see today is a recent phenomenon, a brief, glorious burst of geological life in an otherwise long frozen existence. It implied that the window for life to emerge and evolve in this ocean would be tragically short. Life on Earth took billions of years to progress from single-celled organisms to the complex biosphere we see today. If the ocean of Enceladus was a fleeting feature, the chances of it hosting anything more than the most basic microbial life seemed to plummet. The moon became a poignant symbol, a world with all the right ingredients for life, but without the most crucial ingredient of all time. This was the prevailing narrative for over a decade. Enceladus was a magnificent dying world, generously seeding the rings of Saturn with its own lifeblood, but in the process signing its own death warrant. It was a beautiful but ultimately doomed paradise. The human story of this discovery, however, was not over. The legacy of a great mission like Cassini is not just in its initial findings, but in the decades of painstaking analysis that follow. The complete data set from its 13-year tour of Saturn is one of the great treasures of modern science, and within it, a team of researchers found reason to question the old story. They revisited the original measurements of the plumes. They knew that Cassini had flown through these jets at incredible speeds, often well over 10 kilometers per second. Accurately measuring the density of such a tenuous, fast-moving cloud of particles was an immense technical challenge fraught with uncertainties. The original models had to make certain assumptions about how the gas and dust would interact with the spacecraft's instruments. The new team of scientists, armed with more sophisticated computer models and a more complete understanding of the entire dataset, began to recalibrate those old assumptions. They focused on a particular phenomenon, the drag experienced by the spacecraft as it passed through the densest parts of the eruption. This physical drag, a tiny but measurable deceleration, provided a direct, independent way to calculate the mass of the material it was flying through. It was a different method, a new lens through which to view the old data. What they discovered was a quiet bombshell. The new analysis revealed that the concentration of material in the plumes, and therefore the total mass being lost to space, was far, far lower than previously estimated. The earlier calculations, it turned out, had likely been an overestimation, perhaps by as much as an order of magnitude or more. The immense hemorrhaging wound we thought we saw was in reality a much smaller, more sustainable outflow. The geysers were less like a fire hose blasting uncontrollably into space, and more like a fine, persistent atomizer, a steady mist. Returning to our analogy of the planet-sized soda bottle, the old paradigm pictured a huge gash in the cap, causing the contents to spew out in a catastrophic, short-lived event. The new finding redraws this picture entirely. Instead of a gash, imagine a microscopic, precision-engineered nozzle. It is still venting material, still releasing pressure, but it is doing so with remarkable efficiency and control. The leak is not a sign of imminent demise, but a stable regulatory process. This single crucial revision changes everything. It rewrites the biography of this extraordinary world. If the rate of mass loss is dramatically lower, then the lifetime of the ocean must be dramatically longer. The water world of Enceladus is not a temporary feature, a fleeting spectacle in the cosmic darkness. It is a stable, persistent, and ancient environment. The implications of this newfound stability are profound, rippling outwards through our entire conception of habitability. An ocean that is not tens or hundreds of millions of years old, but one that has potentially existed for billions of years, is a completely different kind of biological laboratory. This vast expanse of time is the master ingredient for evolution. On our own planet, the first simple life forms arose relatively quickly, but it took nearly 3 billion years for complex multicellular life to appear. Time allows for trial and error. Time permits evolution to explore countless biochemical pathways, to build complexity layer by painstaking layer. A stable billion-year-old ocean on Enceladus provides a stage vast enough for a truly grand evolutionary play to unfold. It opens the door to possibilities far beyond simple microbes. It allows us to speculate with a firm scientific grounding about ecosystems, about food chains, about organisms adapted to the eternal darkness of an abyssal alien sea. This discovery forces a radical redefinition of the habitable zone, that traditional concept of a narrow band around a star where liquid water can exist on a planet's surface. Enceladus demonstrates that this zone is not the only place to look. Habitability can be generated from within. The immense gravity of giant planets like Jupiter and Saturn can create tidal habitable zones, warming their moons from the inside out and sustaining liquid oceans in the frigid hinterlands of the solar system. Enceladus is not alone. Jupiter's moon Europa is thought to hide a colossal ocean containing more water than all of Earth's oceans combined. Even distant Triton orbiting Neptune shows signs of cryovolcanic activity. These ocean worlds represent a new and incredibly exciting frontier in our search for life. They may in fact be the most common type of habitable environment in the galaxy, outnumbering Earth-like terrestrial planets by a significant margin. So let us journey there now in our mind's eye. Let us descend through the 20 kilometers of hard crystalline ice. The pressure builds, the faint sunlight from the distant sun vanishes completely. We pass through the boundary from solid to liquid and emerge into the global ocean of Enceladus. We are in a realm of absolute darkness and unimaginable pressure. There is no up or down, only the gentle pull of the moon's weak gravity. The water is cold near freezing, but it is liquid, and it is ancient. This water has churned in darkness for eons, its chemistry slowly shaped by interaction with the rocky core below. We drift downwards towards that core, the source of the moon's vitality. And there on the seafloor we see them, chimney-like structures shimmering with heat, glowing, not with light but with a vibrant chemical energy. The hydrothermal vents, black smokers perhaps like those in the mid-Atlantic ridge on Earth, belching clouds of dark sulfide-rich minerals into the water. Or maybe they are like the Lost City vents, towering white carbonate structures, cooler and producing methane and hydrogen. Around these vents, could there be life? Perhaps we would see vast mats of single-celled organisms, a shimmering, colourful biomass coating the rocks, feeding directly on the chemical soup emanating from the planet's core. This is the base of the food chain. And where there is a base, could there be a pyramid built upon it? Could there be grazers, alien equivalents of shrimp or snails, slowly moving across these microbial mats, consuming them? Could there be predators sleek and adapted to this high-pressure darkness, hunting these grazers in a lightless, silent ballet? The stability of this ocean, its ancient nature, allows us to ask these questions. It gives us permission to imagine a complex, established biosphere, an ecosystem that has had billions of years to evolve and diversify, completely isolated from the light of any star. The discovery of such a second genesis of life that arose independently from our own would be the single most profound discovery in human history. It would answer one of the deepest questions we have ever asked: are we alone? It would tell us that life is not a fluke, not a miracle unique to our small blue world, but a natural, perhaps even common outcome of cosmic chemistry. It would mean that the universe on a fundamental level is geared for biology. Every star in the night sky would look different. Every planet we discover would be seen through a new lens of possibility. The philosophical and spiritual impact would be immeasurable. It would recontextualize our entire existence, placing us within a larger living cosmos. This is the true promise of Enceladus. It is not just a target for planetary science, but for all of humanity. And yet, for all our speculation, we remain frustratingly distant. Cassini gave us a tantalizing taste, a whiff of the ocean's potential. Its instruments were remarkable for their time, but they were not designed to be life detection experiments. To answer the ultimate question, to find out if anything is actually swimming in that dark ancient sea, we must go back. The scientific community is already dreaming of the next generation of explorers designing missions with Enceladus as their singular focus. Imagine a spacecraft, an Enceladus Orbilander, arriving once more in the Saturnian system. This time it would be armed with instruments of exquisite sensitivity, 100 times more powerful than Cassini's. It would enter a low orbit, repeatedly flying through the heart of the plumes. Its mass spectrometers would hunt for biosignatures, the telltale chemical fingerprints that life leaves behind. It would look for specific ratios of amino acids, for complex lipids, for the subtle but undeniable signs of biological processes at work. After months of this orbital reconnaissance, mapping the plumes and identifying the most active fissures, the mission would enter its final, most thrilling phase. A lander would separate from the orbiter, beginning its slow, careful descent towards the scarred south polar terrain. It would navigate towards the edge of one of the tiger stripes, a place where the fresh ocean spray constantly rains back down onto the surface. Touching down with a gentle puff of vaporized ice, it would begin its work in one of the most alien landscapes imaginable. The surface temperature is 200 degrees below 0 Celsius. The sunlight is 100 times fainter than on Earth. Saturn would hang in the black sky like a colossal banded ornament. The lander would drill into the freshly fallen snow material that was liquid water in the ocean just hours before. It would draw these samples into an onboard laboratory, a miniaturized chemical and biological analysis suite of incredible power. There, on the surface of that tiny moon, nearly 1 billion miles from home, it would perform the tests. It would search for cells, for DNA, for the complex polymers of life, and it would transmit its findings. A stream of data, a whisper across the immense void of the solar system, traveling for over an hour at the speed of light to reach the deep space network on Earth. In a control room, scientists would watch as the data resolves into numbers, into graphs, into confirmation. This is the dream. This is the future that the newfound stability of Enceladus's ocean makes possible. It transforms the mission from a hopeful search into a targeted investigation. We are no longer asking if Enceladus could times have been habitable. We are now asking if this stable, ancient and persistent habitable environment is in fact inhabited times today. The revelation that Enceladus is not dying, that its plumes are a sustainable feature of a long-lived world, is more than just a scientific update. It is an invitation. It is the cosmos telling us that one of its most promising secrets is also one of its most patient. The ocean is not going away. It will be there waiting for us, waiting for our robotic emissaries to descend through its icy shield, or to simply taste the spray it so generously offers up to the cosmos. The story that began with a fleeting glimpse by Voyager that blossomed into a revelation with Cassini now points toward a future of discovery that could redefine our place in the universe. Deep beneath the ice of a small Saturnian moon, in an ocean that has churned in darkness for billions of years, an answer may be waiting. And now we know we have time to go and find it, undefined.